Hi, this is Austin with the last video of the year. So the first thing I'm going to do is I'll just run through the whole game to show off all the features, and I'm launching in debug mode so that I can show off the memory heap at the end. I have my start screen. I also am using sprite strings here now since I finally got around to actually putting that in. So these are not part of the JPEG. They're part, or the PNG, or the TGA rather. They are part of the sprite string TGA. So first I'll load just normally. So I have my two types of enemies in this level. I have the one that shoots from a distance, and then this one that follows me. So obviously this guy will just come closer and closer and try to hit me directly, which will do 3 damage. So, and that differs from these guys, who if I get too close will actively try to get away. You can still close the distance and run into them. That's my death scene, by the way. So that's the difference between the two enemies. There's some other details about the shooting enemy that I will go over as well, so I'll start over. Y'all also may have noticed I'm using the particle system for the deaths, and that's the only actual particle effect I have, but there is potential to add more. So bullets will create that effect when they hit the desired target or the terrain. If they despawn naturally, they will not. So that guy just goes away. So like I said, these guys will back away. They'll also not keep moving towards me once they get within range to shoot. That's on a 3-second timer. Also, you'll notice that if I come over to one of these walls and try to run into it, I will just stop. So there's that. And the enemies, I will try to demonstrate, also will stop if they come over to the wall. So if they'll continue trying to back away, but they will just stop at the wall and be stuck. So that should be all the stuff worth noting with the enemies. So I'll go ahead and kill them off and move to the next stage. All of these are, well, the enemies are all using OBBs. The tank is also using an OBB, and then the bullets are all B-spheres. So the enemy manager, once I kill him, will move on to the next stage, and that's indicated up at the top, by the way. So these trees are AABBs, and they don't really do much. They just sit there and can take hits. The main reason I have them here, the idea was to have some cover between you and the enemies, but usually you just kill the enemies before they get here. So the only reason they're coming close is because I've been talking. The main reason I wanted this was to demonstrate AABB collision. So the B-spheres you can see work. ABB versus OBB there works. I'll go ahead and kill these guys now. And here's the last level with the boss. I'll go ahead and also here and demonstrate something I haven't already, and that is the fact that you can change the angle of the shots that you fire with the Q and E key. So the reason I do this is because it's pretty easy. My preferred strategy for this boss is to rotate around him like this to dodge his bullets, which do 2 damage rather than 1, so they're pretty dangerous. And if you go in a circle like this, you can hit him by shooting to the side and just rotate around him. You can also see 4 enemies here, but once the boss dies, the level ends. That's something I did special, was to have 2 different states for the enemy manager that would determine how they work. And so that takes me to my win screen. I now have the ability to restart or quit. I will restart real quickly to show off my my personal project, since I haven't really talked about that yet, and that would be the pausing and unpausing. So I'll go ahead and shoot some stuff just to demonstrate. So I'll pause. That saves all the alarms, all the world data, and everything for the bullets, the enemies, and the tank. So the game objects themselves are destroyed, and now when I unpause, everything comes back to the spot it was. The alarms are all the same still. Yeah, you can see that everything just goes back to where it should be. The alarms, everything just stay the same. So that's done using serialization and deserialization to set a static buffer. So there is a certain amount of stuff that can be stored in that, since it's an array of chars, but I have that as a value that can easily change, not necessarily by the user, but just in case I decide to increase that for theoretical future versions of the engine. And another neat thing, and this one's a bit less consistent, but if I hit backspace, it'll export all of the data to a file. Now I can escape out, Well, I guess while I'm here, I'll talk about this. And there's nothing here except for the stuff that is related to RapidXML that we talked about already. So that's all good. I just wanted to demonstrate that, and I'll move back to what I was saying. So, okay, so I'm just going to take the saving and loading from file from the start. So I'll load back in, shoot some stuff around, pause, backspace to export, escape, start without debugging, bam. So you can see that everything came back even though I fully left the game and everything still works fine. Now, granted, I have been having trouble with this for quite a while now, and I think it's mostly to do with how I'm using fread and fwrite, so I'm still a little skeptical, so I'm going to try this a few times, but occasionally it seems like the amount of bytes read is off by 1 or 2, so, and it looks like it's finally stopped happening, but occasionally that would result in the tag being off by a byte, which would mean it wasn't read properly, which would mean the enemy would spawn in its default position, or the values would be all corrupt if it were in the other direction. So I was having all sorts of problems with that. And my final solution to that was to take... I tried quite a few things, really. I fully removed the files in between each write, even though you shouldn't have to do that because fwrite should do that anyway. But just in case. I also have it using 2 files, which obviously you normally would want it all in one big file, but I was really trying everything to make this problem stop happening. And last but not least, I originally was using the size of, calling that on the buffer here. Now I'm using buff length instead, which is the set size of the buffer, because it looks like the buffer size of can return less than if the buffer's not entirely full. So that was something I discovered the hard way. So... but at least now it all works like it should. Yay! Okay, so that should be sufficient, I think, on that front. So the first thing I'm going to look at is actually the sprite font, since it technically wasn't done last time at the end of Engine 1. So here's the .h file, and again, this is back when we had a lot more direct code to work on, so none of this should be really too surprising. Like, you gave us this directly even. But the glyph creation, delete the sprite font, goes through, deletes every glyph. Sprite string just also should be pretty similar to what you're expecting. Just takes a font, or you can also give it a font string X and Y. Get width and height, set width and height and all that. Here are the functions for that, and then the render just loops through, sets each position, and then increments position by the width. So that's how that works, and I am using that in the start scene and all the other scenes as well, so you can see, oh, it's in the backgrounds, not the scenes, so backgrounds, start BG. You can see here the 2 sprite strings and the text that they display, and you saw that when I showed off the demo. So, and the other thing that I improved on since last time is the God camera, which wasn't working quite right at the end. All I really needed to do was give it a pointer to the tank that is set by the scene. Then it goes through, uses the tank to get the rotation, and then takes away the initial angle, which is pi over 2, and then it multiplies the position and the look at by that, or rather, it multiplies the vector that will be incremented by that new matrix. So that way it also takes into account the Y rotation of the tank itself. So, just to show off what I mean, so if I turn this way and use my forward, it'll go at an angle rather than just going along the y-axis, or along the z-axis, which is what it would have done at the end of Engine 1. So, there's that. So here you see a little class diagram of the different collidable types. Everything on this side should more or less be the same. It's over here where things start to get interesting. So I have the collision volume B sphere, which is very similar to last time, but now I have the box superclass with all of its fields and methods, and the subclass is both derived from that, with them radically changing how all of these are actually implemented. And I'll go ahead and look at those now. I'll linger here just for a bit so you can actually look, and here's the collidable class. So all this registration is all the same. The big difference is now there's always a default sphere, so I have to delete those. I check here to make sure that my current volume is not already the default sphere, and if it is, then I set it to null pointer. So these both checks are to make sure that the collidable volume was actually assigned, because not every game object is going to use their collidable. So I check that. If they have been used, then I delete them. And then up here with the collider model, I do a switch statement to determine what kind of volume type I have and create the volume based on that. So I don't create a new sphere if I already have one, because I always have the default sphere. No reason to make another one. The only real downside is the added if check down here to determine whether or not I have the same sphere twice, but I think that's a worthy trade for the amount of memory I'm saving. So here's just the volume type enum, bsphere, AABB, and OBB. So the collision volume bsphere should be the same pretty much, but there it is. The box superclass is here. So I have the world, the adjusted world, which is used specifically by the visualizer, the min and max, the translation, rotation, scale vectors, the half diagonal, the center, and the scale squared. And then I have getters for most of those as needed by the collision checks, which I'll show off in a moment. So there's that. Here's the AABB implementation. At first, this was not working, but I have gotten it fixed now. Well, I mean, what I mean by that is a lot of this math is going to be the same, but then the check down here to find the half diagonal, or the center rather. I was originally trying to do it with the new max and new min, but just using the original max and min seems to make the math work fine there. So there's that. That was what I changed in order to get AABB versus OBB collision working, which is something that that hadn't been done for quite some time, but now it is. The scale square is the same. And something I just want to draw attention to is I have this initialize data function here to do anything that only needs to be done when the object is created. So for the bsphere and the ABB, that's nothing, but for the OBB, which I'll show in a minute, there's some stuff that you only have to calculate once. So I can compute data based on a given bsphere. I can compute data given 6 floats. Obviously, I can compute data given the model matrix, which is the most likely one. And then the send collision command just adds the command for the ABB collision command. And the OBB. So like I said, you only need to calculate the half diagonal once. You need some default values from the compute data to do that, so I call that here, and then use that data to set the half diagonal and the center, which never, well, the center changes again, but the half diagonal, you can see, I never calculate again. So there's that. Send the command again, so I guess we can actually look at the commands now. So I guess I'll leave that open for now. So I have factories for all of these, by the way. I'm not going to look at every single factory because they're all the same pretty much, but I'll look at all the collision commands. So I guess the C++ would be better. So I call the visualizer display, then I recycle the command on execute. And that's going to be more or less the procedure for a lot of these, but I'll go ahead and show each one. Same and same. So there's that. And then there are the actual commands for determining collision down here in the rest of the collision system that I did not rep here because there are no direct pointers to the collidable group and such, only an array, or a list rather. So game object properties. Let's see. Yeah, here it is. Collidable group for one, commands also, collision testing. Just grab all of these, and I'll go through one by one. So the collision test terrain only needs one object. or one collidable group rather, and it just goes through and calls the and it uses the terrain iterator, which I had shown off before, but I'll go ahead and open that. I will go ahead and open that now as well, just to show off that everything's properly decoupled. So I use that to increment. I go through each square in the terrain. If I get to the end of the terrain, I go to the next row, except with the last row. If I'm in the last row, that's how I determine that I'm at the end. Shown... Yeah, here it is. That's shown in the terrain rectangle area with the begin and end return terrain iterators. And if that is equal to the very last one, then that's the end. So, and then the begin just goes to the 0, 0. So that's the terrain rectangle area. That shouldn't really be anything surprising. And this really shouldn't either. It's just for the sake of keeping the terrain command out of there. So that's that. Here's the execute. You can see that I do have a series of checks to determine whether or not it's colliding with the AABB, and then with the actual object. So this test self command also only has one, and it has a p dispatch as well, which is something the terrain doesn't need. So you can see here that I only need to check, I don't need to do the nested if check from the pair command because it's only one set of objects. But with the pair command, I have to go through a series of checks here to check against the, what's it called? The AABB of each collidable group. Then I check the volumes against the default spheres. And then after that, I actually do the intersect check. So there's the base class, really nothing exciting there. Collision dispatch is here. And that's just the template class from last time, but it's part of the collidable. So just in case, I'll show it again. And the collidable group, here's the whole compute AABB, and then I can get that down here, which is the main change from last time. So there's the math that I got for that. And then I send the command to the visualizer as well. So there's that. And the .h class for that. So that should be everything for the collision. Actually, there is one small thing with the collision that I forgot to show off, which is in the manager. You can see here that I do the compute AABB for each collidable group. You'll notice that I do that before any testing of the collision. So it's only done once per frame, and that is here. I loop through. Note that this is a separate variable because I only need to go through the active groups. There are some groups in the collision list that won't have been initialized yet, so I just stop once I get past the, once I do all the collidable groups. So, and if it's not null pointer, just in case, there will be occasional things where one of the collision groups won't be used in the scene, so I have to check whether there's a null pointer, and if there's not, I will compute the AABB for that group and then move on. So that's that. And that should be everything for real this time. So next I'm going to look at the two systems that are related to the collision but aren't explicitly part of the collision system, that being the visualizer and the math tools. So here's the .h file for the visualizer. It has 3 lists for bsphere, AABB, and OBB. Theoretically, this could probably all just be one list, but I decided to do it this way just in case for some reason you would only want to render one type of collision volume. So I have the delete private that can be called by the attorney shown here, and I'll go ahead and pull up the attorney as well just so you can actually look at it. Visualizer attorney here. So that's for showing, which can be called by the collision commands that I already showed off, and 2 separate types of show AABB. We'll go into that, and then visualize all, and then separate delete part that can be used by the engine class. So here are all the functions. So you can see that I don't actually have public versions of these because they're all used by commands. And then I do have add command functions, though, that can be used at any point. And that's that. So the actual classes, Oh, that's math tools. Here we go. So, starting from the top, I create my sphere and box. Those are the only times they're created, and every other time uses these 2 pointers. So, just to be clear, same with the shader. Everything that needs to be created is created once here on create, or on initialize, that is. So I have the show B sphere, which gets the radius in the center from the passed in sphere, puts those into the world matrix and passes that into prive render B sphere. Prive render ABB just gets the adjusted world and the color from the given ABB and passes that in. I can also, here's the second variant, that if I only have a min and a max, I can pass in that as well. And then the OBB is the same, pretty much the same process. I even use the same class because it doesn't actually matter, because they both render a box. I guess I could have named it something more clear, but I didn't. So, and then show volume is here. It just does the debug view. So, I'll just demonstrate that real quick. Go to definition. So that's where I actually call into the visualizer attorney. So back to here, and where that is used down here. Well, it's used from the attorneys for all this, or the commands rather. But I go through each list, execute every command, then clear that part, and I do that for all 3 lists. And then back up here are the private variants, where I just take the world, the color, and use that to render the graphics object, and I do that for all of these. This one's a little different because I have to calculate the translation scale based on the given min and max, and I could have really done this in the public or the private one, but I chose to do it here. Calculate the world, and then get the color, and just do that. And the delete clears everything. As you could see from the fact that I wasn't leaking it in memory anymore, this is everything that needs to be deleted. So that's that. Now for the math tools. So here are all the functions I end up implementing, all the various intersect ones, and then my helper functions for clamp, clamp point, test overlap, SAT check, and projection max. So the intersect is just the intersect except call to the collision volume. That's just the callback system that we talked about in class. Here is an actual intersect function now. Is the intersect between 2 B spheres. You just get their centers. Magnitude, is it bigger than the radius? If not, then they're colliding. B sphere versus ABB, just you clamp the center to the ABB and then check against the radius. Next, there's the intersect B sphere versus OBB, which is more or less the same process, but you gotta move the OBB stuff into the, well, actually you move the center into the box attorney's local space rather. But at any rate, other than that, the math itself is the same. So, and I just noticed this, so I am going to fix this real quick because that's silly. There's no reason to do it that way. But other than that, it should be the same, just with a couple extra lines up here to get the inverse, and then move it back afterwards. So the intersect ABB versus ABB just involves testing the interval lap on each min and max value for the X, Y, and Z. So that's that, and I'll show that actual function further down. The intersect between ABB and OBB is the biggest because I have to create all 1, 2, 3, 4, 5, 6, 7, 8, 9, 15 vectors. And I do the SAT check on all of them, and if any of them don't work, then it's turned false. So once again, I can really just do it that way. There it is. And I know that I did the same thing down here, and theoretically I could have just done this as a collision between 2 collision volume boxes. But for the sake of simplicity, I just left it this way. So there's that. And then the intersect between a vector and an AABB is important for the calculation. So that just, you check whether the min or max is between the min and max xy's for the AABB. Same process with the OBB, except you move the vector into local space to do that. And then clamp is just fairly self-explanatory. I don't really feel the need to elaborate. Clamp point just clamps all three x, y, and z values. Test interval overlap, just all it's doing is, once again, I'm noticing quite a few of these. I can tell I wrote this last quarter. So I'm gonna fix that real quick, but you should be able to see the process. So the SAT check, this time it is important to do it separately, because if I do the return check in here, but if it's big enough in the first place, or if it's within this value, then I just return true by default, as we were instructed to do. And then the projection max is just here, and this is all just the calculation from the geometry class back in fall. So it's pretty much directly. There should be no big surprises there. So the next thing to show off, and it's totally not a change I just made 5 seconds ago because I read the document again, but I fixed up this so that it no longer will throw an error if you are out of range of the terrain when you're trying to test against terrain collision. So now, if the target cell is larger than the total size of the array, which is done with this math, which is just the amount of squares, then it just computes an AABB with all zeros, which should be impossible to collide with. So if I actually launch in and go over to the wall now, I'm going to kill these guys too, so that I don't die while I'm trying to do this. But I'll come over to the wall. Once I get close enough, I am going to rotate like so. You can see the terrain ends out there. I'll shoot through. It keeps going, and no crash, nothing. So do that a few more times, and nothing. So that works fine. Obviously, there's nothing actually to collide with over there, but at least the game won't crash when I try to. So there's that. So next up is the terrain system. So here are the 4 classes associated with that. Well, 3 classes in a struct, but the terrain object manager is just the resource manager, and it's not directly connected to the other 3 because its terrain object pointer is in a pair that I type defined, so I cannot directly point that to there, but that is a terrain object. And it's just the default path to get the height map, the iterator, the map, the pointer instance, all the stuff that you'd see in a resource manager. The terrain manager, I can get and set the terrain and draw the terrain. That's a scene level manager, and then all this various stuff in the terrain object. So I have a length, a width, the model, the length of the side, like how many like squares there would be on one side rather. So I can draw, I can get A, B, I can get X and Z length, I can highlight all the cells, I can highlight a single cell, I can call intersect between that and a collidable, and I can snap to cell, which just takes a point. Well, I mean, I'll show it off, I don't need to describe it now. And then the min-max data is this struct containing all the data for the min-max for each vertex, so that's in there as well. So the actual terrain object manager is here. It's nothing exciting, and all I'm using for the default path, I put the height maps in with the other textures. So there's that. The attorney's here. All it is just to call the delete, like all the other resource managers. I don't really need that anymore. So here's a terrain manager. So it's literally just if the terrain exists, then draw it. It's a very basic manager, but it still needs to exist for obvious reasons. So there's you can see the one-liners are in here. So there's that. terrain object. Now this is the big one, and I already showed off the rectangle area and the iterator, so I'm not going to go through those again. But the min-max data is just there. All of the various data that is kept by the terrain object, big 4, plus the actual copy and assignment operator are both deleted. So here's the actual constructor that I am using. Draw function, highlight, snap, face, highlight all cells, all the stuff that I already looked at. So let's take a gander. So I set the length to past in length. I set 3 image width height, and I set those integers here. Well, I don't set them, but I define them to be used later. Data type. So I do the read TGA bits as we described using the past in values. Or I don't use them as past in values, but I get them into those values, get the resulting data in those values. I assert that the image length and width actually exist. Set the side as the image width so that I can use it later. Pixel width determined on load is 3 bytes because not using alpha. So the number of verts is just the side squared. I use that to determine the vertex array. Number of tries is just the amount of squares times 2, shown there. I do the whole loop through. This is all in the graphics class, and so I don't really feel the need to go through all this again, but it's the generate the normals here, although ultimately I didn't end up using them really, but that is the process to create them. Tries, AABBs, which is a new thing. I just loop through and use the min and max on the surrounding points to determine the AABB for 4 points, for a square, that is. And then the model is created, and after that I delete both lists and then submit to draw. So the textile index is just to convert, shown there. Again, I don't really feel the need to elaborate on that. Draw is also there. So I guess I can go ahead and comment all of this out since I'm no longer using the that's to show every AABB, and that would lag it out if I left it on casually. So while I'll probably leave the other ones on for demonstration, those can go. So the highlight cell is just finds the one target cell directly below a point, and I also return it, and actually, of course, draw the AABB for the highlighted cell. Snap to cell is here. What it does is you take a point and it gives you the same point except aligned to be directly on top of the terrain. So if you have a point like 500 above the terrain, it'll be the same x and z values just at the same height as the terrain. And I use that so that the players and enemies can snap down to the terrain. And it's not just down, it can go up too, but I mostly just drop things really high in the air and let them snap down. So we'll see that eventually. They get the face normal. So yeah, I end up rolling with just face normals for now. I'm going to eat the points on the barycentric because I just didn't really have time to actually get it properly working. But the face normals work fine. So, and there's the code for it. So like I said, I don't really use the normals here, so I don't need them. But you can see some debug code that I left comment about that I can probably get rid of now. So I check what triangle I should be measuring based off of and use those points to determine the max, temp, and min, and then return that. So that's how that works. And then highlight all cells just takes the min and max of collision volume and then highlights every cell under that range that collides with it. So that's all demonstrated here. And then the intersect is here. You can see again that there's no direct usage of the important data in there. So, okay, so I actually had to verify because I actually got confused when I saw this still. I was wrong. This is not okay. This is the code that I shouldn't have, but it's not actually being called by the engine to determine collision. Like if we look back at collision terrain, okay, here we are. Yeah, if you look at collision terrain, you'll notice that never ever do I actually call the terrain's intersect function. I just left that there as legacy code from the initial implementation of it. So yeah, obviously, if I were calling that code, then this would be very, very bad. But it's not, and I verified that, so I could probably even take this out entirely. Let's give it a shot. Okay, yeah, so that function's gone, and it still compiles, so I actually forgot about that. Should have double-checked that, but now you get to see a little behind-the-scenes work. And that should be it for the terrain object now. That should be everything. The only other things that I kind of glossed over were the get AABB for a given x and y value, plus the start value. I can get the x length and the z length. So, and that should be everything for real. So next up, I'm going to discuss my storable personal project. So this one is fairly user heavy, so I do have some of the files from the game loaded up here, but I'll go ahead and talk about the actual structure first. So the storable is just another parent class like the updatable, drawable. It's not part of the game object. You have to add it separately if you want something to be storable. But all the functions it actually has are just store and recreate, which should be overloaded by the user. The storable manager is a lot bigger. So here's a storage node first of all. This is what is passed into store and recreate, and it's used to actually store the data. So I have a tag here to determine what kind of object it is, and then I provide the user with 2 matrices, 2 vectors, 4 floats, and 2 booleans, and then alarm data. So that I felt like would be a pretty good amount so that you could store whatever object you need to store. Obviously, you're not going to be able to store everything in here if it were a more complicated game, but that's something I could easily adjust at a later point. So, storable manager is here, big 4, and then it's a singleton, so the instance stuff is there. But the actual important functions, well, first here are the actual variables are the tag length, which is 16, the number of storable objects, which I currently have set as 32, which would be more than enough for my game, but theoretically for an actual game would need to be bigger. I have my buffer length, which is just the size of the node times the number of objects, plus the tag, plus an extra integer from when I was storing the storage count in there, but I no longer am doing that. But just in case I ever switch back to that implementation, I still have it here. Obviously, I'll be done after this, so that won't happen, but theoretically it could. Then the buffer, which is where I actually write everything, the count of stored objects, and then the current index of what object to store. So the actual store and unstore really are just as simple as taking the storable object and then pushing it into the list or removing it. Theoretically, this should be done with a reference, much like the other ubbles, but since I've done that for every ubble so far, I didn't necessarily think it was worth the time to re-implement it again, since it's going to be the same process as last time. So there's that. Serialize, all I do is I copy everything to the buffer. I determine the offset. Well, I copy the tag to the buffer. I determine the offset, which is just the length of the tag. Then I create a node. I go through each storable in the list and store in the node, then copy the node to the buffer plus the offset, then increment the offset. I have a check here to see if it gets too big, and if so, then I throw a crash. So that's just a limitation for the user to be aware of. And then I have storage count, and I set it as the size of this list, and then I clear the list. So, and the storage count will become important later when it comes time to recreate the scene. Deserialize, I just take a node, copy everything from the node, and then return the node. And you'll see where that gets used in a moment. And then the read and write from file, I think I already showed off, or at least I described the process. There are some unideal choices here, mostly for the sake of making it work consistently, and that's probably more so due to my trouble with getting fread and fwrite to work as expected, and less because they actually need to be, like having two files for the two separate data, as well as the fact that I'm removing the files. I think I talked about that already. And then I just write everything or read everything depending on the function to the file. I also write the storage count to the other file, and then I close both files. So here's the actual recreate scene function, which is user defined, and it is here because it's not a full part of the user test. It's just something the user will need to write. Basically, you take the you get the tag for the level, not for the object, but for the level. And then you use that to determine what scene you're going to recreate. And that is the same one that is defined here. So the serializable objects also have their own tag, but that's a separate thing. This is for the level. And then you go there, you submit change scene, you set recreate, and what that does is, let me open scene real quick. Set recreate just takes a boolean called recreate and sets it to true, and that is, oh wait, it's not in the scene, it's in the scene manager. Set recreate is here. It sets the recreate function as true, and when you go in to actually look at change scene, if recreate is true, then I set it to false and I call the recreate function. Otherwise I just call a normal initialize function. And the recreate function itself is something that will be called when the scene is rebuilt. So you can see, not there, but here, that if I come down to the recreate function, that it is all user defined. It takes the tag of the individual object and then rewrites it there. So yeah, takes a tag and then calls the here I call create or recreate bullet, or not create, create enemy bullet, given the alarm, the location, and the rotation. Here I actually have special override functions for the tank. So I'll look into the tank manager real quick to show that tank manager. Because the tanks are auto-created at the beginning of the level, and then their data can just be overridden with the new data. So you can see that here I just set the health of my tank manager given the passed in value, and then send everything else to my tank to recreate here. So the store and recreate are both important. The store is just what is called by the manager. It pushes in the color, the position, the location of the pet camera, the scale, the health, the angle, whether or not it can fire, and its alarm data. And then all of that same data is also pulled back out for recreate. And if the alarm is already, or if the alarm is actually been set and it's not 0, then I submit a new alarm. If it is 0, then obviously I don't need to set the alarm because it was never set in the first place. And at this point I realize that I never actually talked about this, so I'll pull this up real quick, is the alarmable check alarm function. This is something that I give to the user to be able to check up on any alarm to determine what how much time is left on it. This is an important thing to use when you're trying to deregister an alarm, because if you don't know whether or not the alarm is already going to be deregistered, you're going to want to check the alarm first and make sure that it doesn't return 0, because if it does, then the alarm is already in the process of being deregistered, and you'll deregister it twice and it'll crash. Now, theoretically, that's something that I could just roll into the alarm deregister already, but I figured that theoretically there could be a chance that the user would know for a fact that the alarm was not getting deregistered, and they wouldn't want to do that because that checking the alarm does require a couple if statements, so you want to avoid those if you can, obviously. So I left it up to the user to determine when they want to check the alarms. So next up is the other part of my personal project, the particle system as discussed in class. I suppose it's not really as personal of a project since it's implementing something you described and not something that I came up with, but it's to compensate for the fact that my own personal project is a little bit on the light side. So here are the particles. It's just position, direction, speed. Particle burst. It has an array of particles. I have 5 per burst right now, but that's easily modifiable. Particle array just is an array of the particles. The scale is gotten from the parent, which is a particle emitter. And the position, range, and scale, the scale of that, and then the position and range of the particles are all initialized from the parent. And I'll show that here, is that I set my scale to the scale, then I go through each particle, get a random direction based on the given range, set the direction, and then zero out the W, and then set the speed. So that is all taken from the from there. And this function is called by the particle emitter. And then down here we have the draw particles, where I go through, I set the position and speed, I set up the rotation matrix, which is going to be different for each particle. Theoretically, that's something that I could store in the particle, but I was trying to stick as close to your original design as possible, so I didn't. Although that will be a little inconvenient, or space-wise, so, or runtime-wise. So, and then I have the translation here. I just set that as the world, and then give that to the graphics object, and then render it. So, there's that. Next up, I'll look at the particle effect. So, a whole lot of gets and sets. Other than that, really nothing to look at in here, or barely anything. I just have an option to create a particle emitter at a given vector, and then I can set the graphics object when the particle effect is determined. And the only reason this can't be a one-liner is because there's more than one thing I need to do here. I need to get the model, the texture, and then set up the graphics object. And then a whole bunch of one-liners for all these various things that I have. I have the particle object, the emitter lifespan, burst lifespan, frequency, scale, range. I didn't have rotation because, as you probably saw, mine just spreads outwards from a given point. So the rotation doesn't really matter since the direction of the heads is going to be fully random anyway. And that's that. Resource manager is here. It's, again, the same as all the other managers, really. There's not much to talk about. The only significant difference is the fact that I don't have a default path, since I'm just getting the data from the particle effect in the effect itself, and that is one of the things that I set. Theoretically, you said to set it from a file, but again, I figured there were better things to do with that time, so I'm just setting it here. You can see that I just set the things here, and I don't need a new path because these just call to the model and I believe the texture manager, but possibly the image manager. And anyway, that's that. I don't know why I opened that. So that's not going to be in the get and load like it would be for for any of the other resource managers. And other than that, it's all the same. It just goes through, deletes everything, and then deletes itself for the delete. The emitter itself, so I set it as a game object, but I'm only actually using the alarmable and drawable parts of that. It doesn't update or anything. And I'll get into why I did that. So, as you can see here, here's the draw. I set all the stuff that I have to set, and then I call draw particles for each burst. And the alarm 0, I have a description of what each alarm does here. So the first one spawns a new burst, then resets the alarm if I have more bursts to create. That's determined by a counter. This removes the first burst, assuming the burst list isn't empty, and then I set the alarm once again. So And then the last alarm, what it does is it recycles all the bursts into the recycle list, and then deregisters itself for drawing its base exit. And that's the big reason, by the way, that I needed to do this as a game object, is because if I tried to recycle on the same frame that I did this emit scene deregistration, there was a decent chance, or a small chance really, but that it would get recycled and then immediately get brought out of the recycle list to be a new thing, and it would try to register for a draw, but it would be in the middle of deregistering, and it would crash. So that was something useful that the game taught me, since I know that's something that we need to keep an eye out for. Yeah, because there could be enough particle emitters on screen at once, since each bullet has the potential to spawn one. That needs to have some sort of delay. And since there's already a delay system built into the game object, I just went ahead and made it a game object using the two important parents of the game object class. So there's that. And then after that, I just clear the burst list, and then I clear the recycle list when it's deleted. And I also have a factory set up for particle emitters. The burst factory is integrated into the particle emitter itself, but this one I decided to keep separate from the particle effect. Not for any particular reason, it was just the way I chose to do it. It's just a pretty normal factory, there's not a ton to say about it. But there it is. So now I'm going to try and go through as much of the game material as quickly as possible. And some of this there's not really a whole lot to say about. Like, all the backgrounds follow the same basic format. They're just drawable objects with a sprite and some text, and all it does is set those and then draw those. So that's all of these, so I'm not going to go through all of those. The controls are also quite simple. They just are inputable objects that take certain button input, like restart takes enter to start the game again, start takes 1 and 2 to determine whether you're starting a new game or loading a game, and then unpause takes enter to unpause, and then backspace to save the file. So that's all of those. So all of those are very simple in their execution. So the enemy and the enemy manager is where things get a little more interesting. So a lot of this is the same as last time. I now have spawn base, ram, and boss enemy, so I can spawn all 3 types of enemies. Despawn just decrements the enemy count and removes the given enemy from the list. And if there's no more enemies, then it really depends on the state, actually, so I'll go into that now. I shouldn't say if there's no more enemies, because that's not always true. Because what it does is the state checks death, and there are 2 separate states, base and boss. Base determines death depending on how many enemies are left given a count, and then boss just determines whether or not the first enemy in the array, which would be the boss, is null pointer, and it'll return true or false based on that. And so that is how it determines whether or not it's ready to submit the alarm or not, and the alarm just causes it to change scene. So there's the override for the save load system, same as the tank manager. And then here's where I set the state. It's just a state type and a switch statement. So that's all for that. Now look at the enemy base class. So can collide with bullet, tank, or tree. It has a health, parent index, store and recreate. So a lot of these aren't going to be defined because they get defined by the subclasses, so but all the draw is the same, the collision is the same, and the store recreate is all the same. So the base enemy is, I showed that off last time, but just in case you want to see it again, so this is just defining all of its models, its particle effect, its collider. Initialize sets up the position, rotation, and such based on a given vector and a given time. What the time does is it can be passed in by the store and recreate, and if it's initializing for the first time, then this value defaults to 0, and you can see that it gets set here, and then later down further, I'll click that to show down further. That's what it uses to determine what alarm to set when it enters the scene. So I can also use this to make sure that the first time it tries to go and shoot, it'll shoot faster than the alarm that it ultimately uses to shoot. So theoretically, and this never happens, but if an enemy were right in front of the player, then it would shoot right away. It wouldn't wait for the 3-second timer to go down. So there's the actual shoot when the alarm is off. It has the update to update all its data. It shoots out a vector to the left and to the right, and then checks the angle of each between where the vector is in the player direction, like the direction between the player and the enemy. And depending on which one's bigger, it'll rotate in that direction. So it'll rotate towards the player in the fastest direction. And this is where it will adjust its position based on how far away or how close it is to the player. And here is where it shoots. It'll try to shoot if it's not currently shooting, and if it's close enough, it'll set fire to true and then set the alarm. So, sorry about the background noise. And then it'll clamp its position so that it stays within the walls. And that should be all for the base. And the boss enemy I'll actually look at next, because it's practically the same process. The only difference is, some of the values are the same, like the scale is obviously different, much higher health value. But the difference of import is where it actually goes to shoot. It'll initialize 3 bullets, one off to the left, one off to the right, and one in the center, so it shoots 3 bullets. And you probably noticed that when I was actually showing off the demo. But that's the main difference of note with that, aside from how each enemy state handles the boss differently. And last is the enemy RAM. And the gimmick behind this one is just that it goes about as fast as the player does, and it skips all of the, let's see, where's the update? Yeah, here it is. So it still does the rotation, but it skips all of the determining whether or not it's too close to move closer. So that way it'll just continue to run up to the player and try to run into them, because that deals 3 damage. So it also only has 1 health, and it doesn't need to set the alarms or anything, because that's all related to firing bullets, which is something it doesn't do. So that's the 3 types of enemies. Looked at the states already. I'll look at the enemy bullet as well. So this is another 3-class situation. The base class enemy bullet determines update, draw, collision, store. And the subclasses determine initialize, scene entry, and scene exit, because the base bullet has a smaller timer than the boss bullet does. So you can see that. Well, my time is set here, so I can't actually show that off, but they each have separate timers. They also do separate amounts of damage. The base bullet does 1, the boss bullet does 2. I showed the God Cam already. So I'll look at the 3 main scenes and then 1 of the demo scenes. Or not demo scenes, but menu scenes. So this is the loose menu. It just has the controller, has the background, and that's all it does. And obviously the real scenes are bigger than that, and I have 3 of those. So I set the tag, or I set the terrain, I set the tag, I defined the 4 walls, I have the tank manager, I reset its health. This is something specific to the first scene, because if the player restarts the game, they should go back to full health. That is after they win. That value is never reset by the game, so it needs to be. It sets the enemy manager as well. It gives both of those the terrain so that the tank and enemy can use those. Sets the God Cam, sets that tank as well. Sets the target on the enemy factory so they can target the tank. Then it determines what the next scene will be for the enemy manager, and then it spawns enemies. And you can see that there's spawn base and spawn RAM given a vector. And then it sets the collision pairs and terrain,
And then the recreate here, I think I looked at this one already, and they're all pretty similar, but calls override for the tank and enemy managers, and then the bullets, it just creates new bullets from the factory, because those aren't created at when the game loads up. So, just to be clear, it calls all the initialization, so the tanks do exist, and then overrides those. So that's why it's different. Base scene 2, same process, but with the addition of the tree manager, plus some extra collision pairs that the other scenes don't need, as well as an extra part of the recreate for if it's a tree. Those can be stored and recreated as well. And then this one is the boss level, so you can see spawn boss plus spawn base. And also, when I set the state, I set it as boss state rather than base state. So, and nothing needs to be different with the recreate because enemy bosses and all enemies are recreated the same way. So that's all the scenes. The scenery is just the walls. They really don't do much. They just get created and they draw. So that's that. Tank's a little more interesting. I'll pull up all the things related to the tank first. Start with the tank manager. So like you can see here, if it's created and it doesn't have health, which it won't at the beginning, then it resets the health to max. Then sets the sprites for the health bar, and then it generates the health bar. So something that I actually didn't note, but the enemy manager also generates a health bar, and that I did separately through an in-game function that I created called draw health bar here. You pass in an XY position translation and a count and a sprite, and it'll do the same math and create the health bar that way. So I have one of each doing each of those so that you can see the difference. To show kind of the before and after, as I was building the engine, I realized that would be something very useful, so I added that in. So that's another thing the game taught me. So that's all the same. Decrement health, all it does is when the health gets down to 0, I kill the tank, and then submit the alarm to determine when to switch to the lose scene. Overrides here, I know I already talked about that. Draw 2D just renders the health bar. That is something that you can also do through the draw health bar function. That's where I have it in the other classes in the draw 2D. I'll actually go back real quick and demonstrate that. Enemy manager, draw 2D, and there it is, draw health bar. So, voila. And that, I think, yeah, that's all for the tank manager, really. The tank itself, it has a tank model, has the textures, all that for the graphics object, particle manager, and it also has a tank turret, which I'll show in a moment, that controls shooting. Here's the initialize. It just sets up the camera, sets up its pet camera to follow it. Then it also sets its own location and terrain. You can see here the snap to cell thing to make sure it actually stays on the terrain when it spawns, since I mentioned that at one point. Calculates rotation here, translation here based on WS, and then A and D for rotation. Adjusts the matrix and sets it as the world matrix, and then displays the visualizer stuff. And I have it labeled as display bsphere, but that's actually set as an OBB right now. So key pressed, I have it to track space and enter. Space shoots, enter pauses, and also serializes all the data in this scene. Draw, it just highlights all the cells under it, and also obviously renders it. Entry and exit, not much to say. Then there's the collision, where it just decreases its health depending on what it ran into. Store and recreate, I know I looked at. So here's the turret, and the purpose here, I originally was going to have a separate model for it, but I decided that wasn't really important enough to get into. So, but what it does is, it has an angle attached to it, and it will get the it'll get its world data from the tank, and then if you press Q or E, you can rotate the angle of shooting, and then here's the set matrices. But then you can, when you hit fire, when you press space for the tank, it calls fire bullet on the turret, and the turret determines what direction to shoot it using the using its own position and rotation based on the given rotation plus its own extra rotation offset here. So, and then the entry and exit's also the same. So that's that. Next, I'll look at the bullet. And this is going to be very similar to the enemy bullet. Same basic process of just it initializes, has a dead boolean to determine whether or not it can actually do stuff. Like you don't want to recreate a dead bullet. So then that's about it really for the initialize. Everything else is going to be the same. Collision, also the same. Really, it's all the same as the enemy bullet, except it collides with enemies instead of the player. And last but not least is the tree class. So this also comes with its own manager. It's the enemy manager, just with less to do. It has a total amount of trees it can track, the current amount of trees, and then the tree array. It can spawn and despawn, but nothing needs to happen when all the trees are destroyed. That's not an important aspect of the manager. The trees are just there to provide some shielding. And then the tree itself. So it sets up the model, it initializes to a location, it draws at that location. It doesn't update because trees don't move. And then the collision determines its health value. So if a tank or an enemy runs into it, it just dies. If a bullet runs into it, it takes 1 health of damage out of 5. So that's it for that as well. So I think that should be everything that I need to talk about on the game end. So if you're wondering why I haven't discussed documentation yet, it's because I will be continuing to work on that after I upload this video. So that should all be in there, and you can build the website and take a look for yourself after I submit all that. So, but this video should cover everything in game that it needs to cover. So, talk to you next time, I suppose, if there is one.